kidding, of course. So today I really am not going to spend too much time on finishing up the rendezvous part with the target planet. I'll describe things at a very high level, so if you're wondering what I can ask you in the test about this last chapter, it's again conceptual questions. Everything that this chapter does doesn't really have anything that is new compared to Keplerian orbits. It's just a use of those tools. So that's why I go quickly on the equations, because it's just a matter of understanding what is the idea behind patch conics. So I want to finish that and then maybe spend a few minutes to say a proper goodbye, and I'll meet probably half of you next semester, right? I see already 40 plus registered for the, what is it called, Aerospace Design 2-1 class. Again, I'm sorry for you guys. They picked me. It wasn't my choice. I'm very excited about that. So it's gonna be fun. I make sure during the summer that there is one specific project nailed down, probably with a customer at Kennedy Space Center, so I'm not the one setting up the requirements of the mission to design, so that from day one we know what we're going to do. The teams hopefully are not going to be more than 8 or 10 people. Last time I've done it this way, it was to the point of actually sending, I probably told you this, papers to conferences. So I think it will be fun. It'll be a chance for you to put together all the things that you studied and create your own design. We're not going to build anything. I'm not even going to try to build anything in a semester. That's impossible, I think. Not even in a year probably makes sense, but in a semester, definitely not. But so, yeah, we'll say goodbyes, and I'll give you a few comments about the class in general at the end. But let's finish this. So we have covered the heliocentric point of view. It's a Hohmann transfer, that's all we do. And then we focus, we disconnect from that, and we say, oh, there is a sphere of influence. I'm coming in with this velocity with respect to the planet, or I'm leaving the planet with this relative velocity. Combine the two, add them up, and get the heliocentric velocity. So if we're still referring to the case where you're going to an outer planet, so say that this is Sun, and this is the orbit of the Earth, for example, and this is the orbit of Mars, we are going to leave on a Hohmann transfer the Earth's orbit, okay? So Mars, Earth, this is what we call the cruise trajectory. It's just a Hohmann transfer. You're going from point A to B. You better make sure that Mars is there when you get to point B, right? And so we have done this part. Let's just refresh what we did there. We said, okay, I'm inside the sphere of influence, and I have a few known things. So the inputs for solving the problem from the departure point of view, where what? What do we have? You have V infinity. You need to make sure that you're adding enough velocity to the velocity of the Earth so that you can leave the sphere of influence and have the correct heliocentric speed to be on the cruise trajectory. And probably you had some initial parking orbit. We just assume that we are at some circular orbit of radius rp. That's a reasonable assumption. So those two things are given. You can't play with those. Rp is your parking orbit where you're starting from, and V infinity is what you have to add relative to the Earth to escape, right? And be on that cruise trajectory. And then we said, okay, with this information, what do we figure out? We figure out the outputs, and those are what? Well, the delta V that you apply on this circular trajectory, right, to go on the hyperbolic path. And then what else? What else do you need to figure out? You're performing a maneuver, right? I'll probably do a little sketch here, assuming that I'm good enough to reproduce what the book has. So this will be your planet Earth, its velocity, and you are on some parking orbit here, and at some point you decide to go on this hyperbolic path that has to lead you, in this case, to leave the sphere of influence with a B infinity that is aligned with the velocity of the planet. That's what we do if we do a Hohmann transfer, right? You can't add V infinity at an angle with respect to BE, otherwise you're not going to be on this cruise trajectory, right? So we said that we figure out the beta angle, right? You have an asymptote here somewhere. So I think this was your beta angle, right? so that you know exactly where you have to apply that impulse. So you know what the delta V is, what you have to do here, but you also know where here is, because it cannot be anywhere else than this point. If you do it here, your V infinity is going to be maybe somewhere on this side of the sphere of influence, and it's not going to add up to V of the Earth the right way, right? So that's what we had at departure. You are given a V infinity, you have no choice, and you are given where you're starting from, some parking orbit. We assume it was circular, it can be something else, but the idea is the same, and you figure out the maneuver and where to do it on that circular orbit. Now, at arrival, what happens? We're going to look at this image here. But what, from the heliocentric point of view, remember the Hohmann transfer, what do you do when you go to from a small circle to a bigger circle? You increase your velocity here. Once you touch the bigger circle on this half ellipse, that is the cruise, what do you need to do here? In principle, you will have to increase the velocity again, right? In other words, if Mars is right here, and this is its velocity, v of Mars, you're coming in with the velocity of your spacecraft, right? That it's a little less than that, right? So if this is the point B, these two objects, with respect to the Sun, have a velocity, they have velocities where the Martian velocity is higher than the spacecraft velocity. Make sense? So again, this is the disconnect and the approximation of doing patched conics. You are just suddenly, at some point here, you say, okay, this is the relationship between the velocities with respect to the Sun. I'm going to switch instantly and look at the sphere of influence. The V infinity is the difference between these two, right? So the V infinity is going to be the relative velocity with respect to Mars. So if this is the velocity of Mars with respect to the Sun, and this is the velocity of the spacecraft with respect to the Sun, then your V infinity is this. And that's exactly why your book says, you basically see, you can imagine the spacecraft coming in from the front of the sphere of influence. It's just a way to say that the relative velocity is opposing the velocity of the planet. This is not Mars, it's just a cold planet too, but yeah, that's what we're assuming, that it's Mars. So, I mean, one way to imagine this is that the planet is coming, it's approaching point B, you're approaching a little ahead of that, and then, the planet sees you coming in from the front. You can imagine whatever you want. This is the approximation of patched conics. Heliocentric, all of a sudden I switch to the sphere of influence. There is a patch right there. Make sense? Okay. So that's our starting point. We are coming in, if we're going to an outer planet, and again, this is just one case, going to Mars. You can go the other way. You can go to a planet which is inside the orbit of the Earth. It doesn't really change the procedure. So what are the inputs? Again, my inputs are, well, V infinity is the same, right? And then, rather than saying inputs and outputs right away, I would like to say, what are my goals at this point? Because my goal, starting from the Earth, was just leaving. I have to go. I have to leave this planet and go on a cruise trajectory. That was pretty clear. Well, here you could do different things. Now you are arriving, you're rendezvousing with your target planet. You can do many things. First one, allow me to write this just to make it simple. You can crash with the planet if you want. Why not? In other words, you land with the planet, okay? You land on the planet. This is landing, which from our point of view as an approximation to compute numbers, indications of numbers, what you do here is that that point P will be where you may maneuver to stop this hyperbolic path and go maybe on an orbit around Mars. So if you want to do this, then you set that RP has to be equal to the radius of the planet, Mars, or 2 in this case, they're not calling it Mars. You can do that. That is a perfectly fine goal. The fact that then you're going to approach that planet with a very high speed, it's a different problem, and it's for people who do thrusters to slow you down, and that's not for us. But this is what will give you an idea of what. Well, you set the RP. I don't know how I can obtain that for now. A second goal could be, going into orbit, meaning you don't want to leave the planet. You want to slow down that hyperbolic path and go into something like that, for example, an ellipse around the planet itself, which is here called the capture orbit. So it's a closed path around the planet. Or you can do something that it's very exciting and it's done all the time, which is amazing. We're going to discuss it very briefly here. You can do a flyby, which means I do absolutely nothing. I come in, the planet is there, is going to turn my trajectory. If you don't burn any thruster, if you don't activate any control, you just keep going, you pass the perigee of the hyperbolic path. Remember, this is all relative to the planet. And then the end result is that you get a V infinity right here, the same magnitude, right? We know that. It's just at a different angle with respect to the planet. So what is the result of doing a flyby? You're just changing the velocity with respect to the sun. And the amazing part is this, just as with that example, let me just draw a couple of vectors and show you. I need to write a couple of formulas just because the outputs here, I haven't listed the outputs here. Maybe I should do that. Let me just open this parenthesis. So what are the things that I can control now to obtain one of these goals? Just to be clear. What things can I control? The V infinity I cannot. This is the only thing I can control. What we call the aiming radius. If you play with delta, meaning you approach the planet a little more at a higher distance or less distance, you're going to make this hyperbolic path closer or farther away from the planet itself. If you make delta smaller, your perigee here of the hyperbolic path is going to be smaller. If you make it wider, you're going to fly by, if you don't do anything, at a higher perigee. That's the only thing you can control coming in. V infinity is given to you. RP, or doing a flyby, but even the flyby will have to have a specific RP. It's given to you. So the only thing you can play with is delta. So we're going to write the formulas to get from these known things to the actual value of delta that you have to select. And I'm not going to dig into the details because it's all expressions that you have seen in Keplerian orbits and you can figure them out. Yes?
So in this view, it shows we're entering Mars like, as it's coming towards us.
Yes. Right. Yeah, exactly.
I'm a little confused because on a more orbital picture you drew, it looks like it's like we're catching up.
Yeah. Well, it looks like, but the thing is that these are only trajectories, right? Where the objects are, and again, this is the problem with approximations, is that some things in some parts may more or less make sense. You may assume that you're actually coming to point B a few seconds before Mars. Think about what is happening. Mars sees you coming towards it. Does it make sense? When they rendezvous, when they meet, so if I zoom in this area here, and this is Mars orbit, and it's coming to this point that I called B, right here, right? The rendezvous point. And the satellite is coming on this other path. It may be very well the case that this object, that it's here, that it's here, that it's here, that it's here, it gets here a little before planet Mars. And in that case, since Mars is flying faster, it sees it approach it from the front. But again, this is something you can imagine or not. We're not solving numerically and with high precision what happens in reality. Because in reality what happens is that the Sun and Mars are both affecting at the same time, all the time, the trajectory of that object. This is approximation of patched conics. I decide that heliocentric trajectory, it's up to the sphere of influence, then I forget about that. I just figure out a V infinity and switch to that. And since V infinity in this case happens to be pointing towards Mars, against the velocity of Mars, because of my calculation, what I did before, V of Mars will be pointing this way, right? And I do know that velocity of the spacecraft coming in, and these are both with respect to the Sun are this way, so the relative velocity with respect to the planet has to point opposite to the planet. That's all I need to know to go there. That's why I put V infinity going up towards the planet, opposed to V2, right? So, make sense? All right, so I'll do it here. The beauty of doing something like this is exactly, look what we were doing before. Before we had, basically at the entrance of the sphere of influence, this is what you have. You have Mars that has this velocity, the spacecraft has this velocity, this is your V infinity, right? And this is the velocity of the spacecraft with respect to the Sun. It's a certain magnitude which is less than velocity of Mars. At the exit, things have changed. You have, I hope I can do it in scale, probably not, Velocity of Mars is the same. Now I'm adding the v infinity, which is some angle with respect to the velocity of Mars. Say that it's this one, right? So my actual velocity with respect to the sun, which is the addition of the two, so this is going to be velocity of the spacecraft right here. Look at this vector. It went, magnitude-wise, it went from being less than the velocity of Mars to obviously more than the velocity of Mars with respect to the sun. Do we see that? Simple vector geometry. So the gravitational field of Mars is working for you to increase your speed with respect to the sun. You come in with a certain velocity with respect to the sun. I don't know what this could be, some number. You're coming out with something that is, of course, at an angle now. Who knows where that goes when you go back to heliocentric trajectory, but it's a higher velocity. That's your delta V. You haven't turned on a single engine to do that. So before I show you equations just to figure out how you get that delta to do the different things that you can do, let me show you this amazing image here about, I wrote down what image it is, 824. It's amazing what people can do using planets. I went way too far. This is chapter 9, of course. Oh, yes. What people can do using flybys. Here it is. Okay, this is the Cassini's mission that lasted 7 years to go to Saturn, and this is what they've done. There is obviously a maneuver here, launched from Earth in '97. This was all designed properly to have all these flybys at the right times and creating the right velocities to go to the next flyby. So this is a lot of work that is done obviously by hands, but mostly by appropriate simulations, and it's beyond our work, but it's exploiting this fact that you can change the velocity because of flying close to a planet. So leave the Earth. There is a first flyby right here, I think, yes, with Venus, which is a smaller orbit than the Earth, and this increases its velocity. The spacecraft has increased velocity. Of course, it's going to this green orbit. Something has boosted its velocity. When you do Hohmann, you go to a bigger orbit by increasing velocity. So that's the same principle. First flyby, which happened when? A year almost after launch. And then you go on this coasting trajectory, the green one, and there is another encounter with the same planet. Second flyby. Another year later, right? Yeah, kind of. Almost a year. More than a year. And this is strong enough to give enough velocity to the satellite to actually go and intersect the Earth's trajectory again. So this is going back and forth. That gives it another kick right here. In '99, that's enough to go and meet Jupiter in 2000, another flyby, and 4 years later you are at the target. The only thing you do there, well, there's obviously mid-course corrections, but in principle, if you do everything Keplerian, you don't have perturbations, and it's all ideal, that is doable just by flying by planets. And I think this is just amazing that we can exploit the fact that these objects are moving around, we just fly close to them and get a velocity in the right direction. So, I mean, if some of you are going to work on these type of problems, this is something to study more in depth, of course, and it's beyond the scope of a class like this. But that's what a flyby does. It creates a change in your velocity, which can be an increase in velocity without using any thrusters. The gravity is doing the work for you. What else can I say on this, other than it's extremely cool? Well, it goes back to the comment, that exercise we had where 70% of the mass of the spacecraft was spent just to leave the Earth and go on a cruise trajectory to Mars. Well, there are obviously other ways. The Hohmann transfer is the most efficient two-impulse trajectory, but it may be too expensive to go so far away. So you can do other things, like in this case, you don't have to do a full Hohmann transfer. You can do shorter trajectories or longer trajectories until you encounter the right planet that gives you the right kick. So it's always a trade-off of time versus fuel. These could have been done probably with much less time than 7 years, but we probably don't have the technology to actually give enough delta V to just go straight to the target planet. We just don't. The engines we have are pretty good, but they're not that efficient. So it's a matter of time, and unfortunately when we have unmanned spacecraft, you can afford it. With humans, we know radiations are a problem, so I don't think any human could survive 7 years in deep space with the current technology. I don't know, but it's always a trade-off. So the flyby it's very, very cool stuff that you will probably see if you go to graduate school in an Astrodynamics 2 class, whatever they're called, Advanced Astro. But let's figure out a few things here. So how do you solve for the delta? Basically, the delta is all I have to solve for, right? Well, it's the same expressions we've seen last time. Nothing new, really. Okay, let's see. If you're doing a flyby, for example, what you want to achieve is a specific, I'm going to show you another image here. It's a specific turn angle, what is called the turn angle. Where is it? 816, no. I know there is probably a more efficient way to find the pictures, but okay. So this is exactly what I said before, is you're coming in with the same V infinity, but as you move your approaching the planet on the sphere of influence up or down, you get a different result. If you're closer to the planet where you come in, you're going to have a lower perigee, and the turn, assuming you're not crashing on the planet, the turn angle, which is the angle between the V infinity at input and at output, is going to be increased because, of course, the gravity is pulling you more, right? So that turn angle, if you're doing a flyby, is given by the usual expression 2 arc sine of 1 over E. And the eccentricity, we have seen this one, it's going to be for the hyperbolic orbit, this expression here. Okay? So, in this case of a flyby, you know what you want. So your goal is obtaining a certain delta, right? So you have to figure out, yes?
Is that delta different than the capital delta that they use?
Yeah, it's a little delta. It's not in this picture. It's probably in the first one that I showed you. Yes, that's a good point. The big delta, the capital delta, is called the A-mean radius, is the distance. Let me see. Yeah, it's right here. I think this has both, yes. So the capital delta is the distance between the direction of the velocity of the planet and the asymptote where you're coming in. So that's the one you want to adjust. And you want to adjust this, in this case, for a flyby to obtain a desired delta. And the delta is going from this asymptote to the other asymptote. It's not, don't look at this, don't look at beta. It's just that angle up there. And that will be how much you're turning the velocity, just because you're flying by the planet, right? So in this case, this is desired, right? And so if this is desired, what you do, you take your desired delta, solve for the eccentricity, V infinity is given, and you know E, you're going to compute RP, right? So from these two formulas, you can compute RP. And once you do have RP, one thing that we have seen last time, you can actually just go here and tell what the A-mean radius has to be. Once again, I do not believe in memorizing formulas. I do know that these things we have seen when we've done Keplerian orbits. You can go back and double check and demonstrate these formulas. It's just geometry of conics. But you need to know what the inputs are. That's the input in this case. That's all you have. That's what you can control and you need to compute. And you control delta, the big delta, so that you obtain, in this case, a certain turn angle when you're doing a flyby. That's one thing you can do. What else? Well, if you're crashing with the planet, well, I just simply do this. In that case, RP is set. You can forget about this expression. So if you're crashing, okay, the crash case, the desired quantity, it's a certain RP. So you use this expression to compute the eccentricity again, because V infinity is given. And once again, you go back to this expression down here. So you actually don't even need to go through the eccentricity. So given RP, you can just go here. And that's how far you need to come in. There is a section in your book that talks about sensitivity of these maneuvers. A small error in these maneuvers has a lot of impact on how off you're going to be, as you can imagine. We're talking about millions of kilometers. You off at the beginning a little bit, it propagates. Okay, that's crash. And then the last one that has a little bit of formulas here is actually going into some kind of capture orbit. And the book and my notes here show what is the ideal capture orbit that you want to go to, meaning the less delta V. Because if you want, so all the things that we have seen, the crash and the flyby don't require any maneuvers, right? But say that you actually want to go into a capture orbit like this, then you have to do something at perigee, of course. You have to slow down that motion. You can't remain on a hyperbolic path, otherwise you just leave. Which parts can I erase? Everything is on the book here. And I told at the beginning, I'm going high level here. I just want you guys to understand the concepts. What are the inputs and what are the outputs? What are the things that are given to you, or what are the things you can compute to obtain the different goals? So if you're actually going to if you're going to orbit, capture orbit, as they call it there. Okay, so the velocity at perigee of the hyperbolic path, dph, I call it here, it's conservation of energy. V infinity is given. You can figure out what is your velocity at perigee. That's what it is. On the capture orbit, so let me call Vp on C capture orbit, same idea. If its eccentricity is E, this is what you will have, mu of the planet, 1 plus C over Rp. Now, this is the eccentricity of the capture orbit, not the one of the ellipse.
C subscript for capture?
Yes, PC. Okay, so the delta V is what? Delta V is going to be, of course, Vp elliptic minus Vp capture orbit. So it's this quantity minus this quantity. What do you expect that it will happen if I start increasing the capture orbit's eccentricity? More and more and more and more. What is the delta V going to do? Smaller and smaller, right? Well, you see from the formula, because it's here, it's a minus right in front of this, and that makes sense. But imagine that this is actually going to eventually match the eccentricity of the hyperbolic path. There is no delta V. You're doing nothing. Okay. So what your book is doing is trying to find what is now the correct Rp, the distance at perigee, which again, once you have Rp, you can always bring it down to the aiming radius. What is the Rp I need and the eccentricity that goes with that on the capture orbit so that this delta V is minimized? Of course you want to minimize this, right? So what is the minimum for this thing? And again, without doing it specifically, what you can do is just rewrite this expression, normalize it by V infinity. The delta V is going to be 1 plus 2 over epsilon minus square root of 1 plus E over epsilon, where this epsilon variable is the one you need to determine. It's Rp V infinity squared over mu 2. So these things are given. You can't change them. You need to find, you want to find what is the, this letter is getting worse and worse every time, right? The epsilon star. What is the right Rp that is going to minimize this function of epsilon, right? So, you know, I have the steps to do it. But let's forget about this. If you wanted to do it, and you can do it in MATLAB, you can do it by hands, I don't care. I'm giving you this expression here, dV over V infinity, and it's just normalized. So it's a function of that epsilon, right? So basically I'm saying that delta V over V infinity is some function of epsilon. How are you going to find what is the minimum of that function? So you're going to find what? This and you're going to impose what? Equals 0. Is that enough? Yeah, I mean, this could be a maximum as well, right? So I'm going to do this, second derivative of this thing, I'm going to make sure that the point that satisfies the epsilon that satisfies this expression also satisfies, positive. Because it means that my function of epsilon looks like something like this at the epsilon star that I'm looking for. So on the y-axis, of course, there is f of epsilon here. And that can be done by hands. I'm not going to bother writing what those derivatives are, because you can do the derivatives of these. You can take them. You can compute those, and I'll just give you the solution. So the best choice is to go into a capture orbit that has let's see. Well, the solution is going to look like this. The epsilon star is 2, 1 minus e over 1 plus e, which, if you go back to the definition of epsilon star, is going to give you the radius at perigee that you need to target. 1 minus e, 1 plus e. So that's your radius at perigee. And also, to make sure that this condition is respected, it comes down to saying that the eccentricity of that capture orbit has to be between 0 and 1, 0 included. So that's one thing you may want to do. If you want to go into an orbit around the planet, do it in an intelligent way. Going to the circular orbit is not necessarily the best. It's actually an orbit that respects this condition. Questions? So let me summarize here again what you do when you come in. You come in with a B infinity. Yes?
What is the y-axis on that graph that you have?
It's the function. Will be in this case the delta V over V infinity, which I just called f of epsilon. Right? Yep. So for the patch conics, this is really what boils down to. You have a heliocentric trajectory that allows you to compute the right velocities at the 2 points, in this case for the Hohmann transfer, and they give you the V infinity. Once you have the V infinity, you switch into the sphere of influence. For leaving the planet, it's really simple. We compute the beta angle and the right delta V from the parking orbit, and you're done. Coming in, you can do more things. Once again, the inputs are V infinity. That you cannot control if you're coming on a Hohmann transfer. It's just given to you. These you can control. Someone has to do fine maneuvering so that you're coming in at the right distance. I think this was one of the problems where one of the, I don't remember the name, one of the NASA missions that was supposed to land on Mars missed the correct aiming radius and ended up just flying by, goodbye. It was never able to actually, be captured because it just flew too far away because of miles versus kilometers. I just can't believe that people still do that kind of stuff. But yeah, someone was talking miles and someone else was talking kilometers, and it didn't work. They didn't understand each other, so this delta was incorrect. I think that was the problem. I believe so. It just ended up going, flying by too fast and not being captured. So you do have this given, you do have control on this. Controlling this allows you to be at the right position at the perigee of the hyperbolic path, which could be the radius of the planet, you're just impacting the planet, or it's a right RP so that you obtain a certain delta if you're doing a flyby. And so the output velocity is what you want. Again, the V infinity, the magnitude of that will be set. It's whatever you're coming in with, but the other side you can control the little delta angle. And the last one is this one. You can enter into an orbit by slowing down that hyperbolic motion and obtaining a standard closed orbit around the planet. No questions? Once again, what to expect on these is conceptual questions. At the most, I can have an exercise where these few formulas I gave you, just the final results could be used, but maybe not even that, because this is really starting to talk about things that are for another class. And I don't want to push it too hard. It was just, the intention was just to give you an idea of how these trajectories are designed at interplanetary level. Do you have any issues, concerns with these? Okay. So to wrap it up, a few things. First of all, I did email AGI. I know that a lot of you are probably still turning in tests, certification tests. So they do say that it may take them up to 5 days to correct them. I made them aware of the deadline of the 20th. On day one, go back to that video I told you it's your responsibility not to push it to the last minute. If AGI is not able to correct it and send me a proof by the 20th, I'm going against my own rule. And I've done it a few times over the class, and I don't have anything against that. It's just that please try to respect the deadlines, because it puts me in an uncomfortable situation to justify people who are not respecting the deadlines versus those who do. So I have a list of those who are certified from them up to this point. I did tell them, please do it quicker than usual, and they'll try. But it's Monday. If you're still turning in stuff today or tomorrow, you're probably pushing it. That's all I can tell you. I can probably deal with individual cases, as I usually do. But this opens another, comment that I wanted to make about the class in general. I think with some of you, I may have looked strict in applying the rules. With some, I haven't, probably. The first case is when I perceive that a student is trying to cut corners or get a shortcut. And I don't have anything against helping students. It's just that my job is not allowing shortcuts, because the moment you leave this place, you may have people who help you in your career and can give you a break when you really have a problem and you can't respect a deadline, but that's probably not going to happen. So from my point of view, my job is done when you guys are independent and you don't need me anymore. You don't need the other faculty anymore. That's when our job is done, when you can be on top of your stuff. So my only justification for applying, in some cases, the rules stricter than in other, well, I do try to apply them across the board the same way, but for some people I may have looked, I don't want to say harsh, but I said, no, you have to do it by this date. It's because that person probably was trying more than once to cut corners, and I can't have that. It just is not fair towards the rest 998 people in the class, right? So I think that that's part of our job. It's just getting people to the point of being independent. You have to take control of the things you do. You want to be completely independent from, as a kid, you want to become independent from your parents, and as a student and a professional, you want to become independent from us. I want, in a few years from now, to talk to you as my peers, where you teach me stuff. That happens all the time, and that's perfect. If you just continue to require help of all sorts because you can't be on top of your tasks, then you're just not going to be happy. That's really my end point, is that if you want to be happy in your professional life and your personal life, you need to be in control. And if you're not in control of your deadlines and everything that you have to do, you're just going to be dependent on someone else all the time. If you're trying to come to me for extra points where you have not earned them because you haven't respected a deadline, you're still dependent on me. You're putting your career in my hands. You're giving me the power to say yes or no. So you're dependent. While if you take control, you don't put yourself in those situations anymore. So I'm just trying to say that, yes, I try to flex when I can, but in some cases I just cannot. I just don't think it's in line with the goal of my job. That's one thing that I want to say. So with the AGI, I hope you guys will be all done by the 20th. And if not, we'll have to talk. Faculty evaluations are up. Last time I checked, I only had 15 people responding. I don't see the responses yet. I only see the number of people responding. Another comment. You're probably old enough that you don't need all these suggestions from me, but if you have a right to vote, you wouldn't believe how many people don't vote. So in Italy, we just had we called it referendum. I don't know if this word makes any sense to you, right? So they were voting about drilling in the ocean to grab oil from the Mediterranean Sea. The thing was just unsuccessful because people didn't show up. I receive, as Italian, I still receive those pieces of paper that I can vote from abroad, and I send them in. People in Italy didn't vote. So the whole thing was millions, if not billions, of euros spent for nothing. People did not express their opinion on something that is important. So if you have a right and you don't exercise it, then you don't have a right to complain. That's what I'm saying. So people just stop caring about voting. You should vote. And the faculty evaluations are not a vote, but it's a way for you to improve what we do. I look at them. I looked at your midterm surveys. I do care. I try to adjust. I'm not perfect. I can't do everything. Can't make everybody happy, that's for sure. And that is really not my goal. But if you don't do them, then it's the same. Outside of here, you don't vote. Then you live with the system that other people decide for you. So you have to have your voice heard. And if in my case you think everything was fine, just do it anyways. It's not like a hotel, on TripAdvisor. You don't write anything if everything was fine. You just complain if there were cockroaches in the bedroom. You don't do that, right? In a class. So I really invite you to do it. And you will be surprised by how quickly in your career leaving college, you will get to a point of having to evaluate your peers. So my department chair evaluates all of us every year at this point of the spring semester. We, 55 people, send an evaluation for the faculty chair, for the chair of the department, I don't know how often, not every year, but we do send our feedback. So it's a two-way kind of interaction. And as you grow up, you will do that more and more often. There will be people asking for reference letters. You guys will probably ask me for reference letters, and please do if you need them in the future. But do these things because they get you connected with other people. If others are starting to rely on you for reference letters and evaluations, that means that you're doing a good job, and they need you. So try to be needed in that sense. But do exercise your rights. I think it's just pointless not to do so. And do it responsibly. I don't mean to say be nice to me, just write what you think it's right. But you will have people who will not be fair with you, and I'm sorry if I've been one of them. It could happen. It could happen. It was not intentional if that was the case. But you will have people who will not be fair to you, who will not be respectful to you outside and in the job environment. That has happened to me several times. One other piece of advice, keep your cool and just be professional. If you have to evaluate those people, just evaluate them on their professional stuff. Keep the personal feelings outside. Personal stuff mixed with job, it's a dangerous combination. Just don't do that, and you will be in good shape. So please do the faculty evaluations because this department has very low responses. I don't know why, but people just don't do it. So this is the end, unless you want me to record more lectures. I really enjoyed teaching this class. I actually asked today to teach it again next year. We'll see, but yes.
The third exam, that's chapter 7, 8, and 12, or is it everything we covered?
It's going to be more on the last things we covered, but I mean, if you need to write the expression for the energy of a Keplerian orbit, that was at the beginning. You should still be able to do that, right? But it's going to be conceptual again. I'll tell you now, and I'm going to tell you on Wednesday, do not overthink it. And I'm serious, okay? Do not overthink it. So I thank you all for this opportunity of teaching this class. I want to thank Patrick because I never seen a TA showing up that often in a class and doing this. This has taken a lot of work on my side to edit the videos and post them, and Patrick's side and Thomas as well. He's been probably grading a little more because of you doing this. So I think it's been very enjoyable. This is my long speech at the end of the semester, I guess. The only thing I want to wish you is be healthy, be happy, take control over your lives and your profession. That's the only way you're going to be, satisfied with what you do. Thanks.